is doing some double duty between Facebook and NYU, and he'll start us off.
All right.
Okay, good.
Great. Well, thank you for the introduction. There we go. Excellent. Okay. All right, so my talk is going to be just a very general overview about some of the very exciting progress that's been made in the last 5 years or so on a range of tasks in AI. And as a result, this has been picked up by the media. I'm sure you've seen various articles about it. And buried in all this excitement is the fact that a lot of these advances have really come from quite a narrow range of techniques within machine learning. In particular, these models called deep neural nets. So that's what my talk's going to focus on. And I just also want to say that, while there has been a lot of progress, we're still really a very long way from solving the sort of general problem of true AI. And there are many challenging problems that remain on that path. And so I'll try at the end to, just touch on a few of them. Okay, so neural nets actually have been around for a very long time. So the current wave of excitement is really the sort of third time that people have got, very excited by them. So the idea originates back in the 1940s. And the underlying principle that underlies all neural nets is that of something called connectionism. And this is this idea that if you take some very simple computational units and you connect them in a very large network, you can get complicated behaviors emerging from them. And so in this spirit, the researchers back then started looking at artificial neurons, which are a very simplified version of the sort of biological neurons, and used them to sort of build very simple models called perceptrons, which are basically a sort of single layer neural net. And they were very much hamstrung by the kind of hardware limitations of the day, but they were actually able to train these things to recognize very simple patterns, as you can see on this, the figure, this letter C on this wall here. And so these models really, the little model I'm showing on the left is really a single neuron, and all that happens there is a simple series of additions and multiplications and some kind of nonlinearity. That's really all the sort of ingredients that you have in each computational unit, but by putting them together, you can actually do something interesting. Now, basically, people realized that with these single-layered models, you couldn't actually do an awful lot, and there was a sort of lull in progress. And then in the sort of 1980s, people figured out how to train models with multiple layers using a technique called backpropagation, and that ignited a whole wave of new applications and sort of performance results. And one particularly interesting model that emerged at the time was a type of neural net that was designed essentially for images. Its architecture was kind of adapted to the structures you find in images, being on a regular two-dimensional lattice and so on. And some of the sort of components within that model were very much inspired by biology, from people like Hubel and Wiesel. And so using these convolutional nets, they were able to show very good results on sort of handwritten digit recognition at the time, and did create practical sort of check reading systems and things like that. Now, that was the sort of second era, and the current era we're in now is really, I guess, started in about 2011. And what we've seen is a whole range of performance breakthroughs on a range of perceptual tasks. So that is sort of computer vision, speech understanding, natural language processing, and things like that. And there are sort of three ingredients, really, behind these breakthroughs that are common to all these different domains. So first is these big, deep neural network models. So they're very much, in fact, the same models from the 1980s, but just much bigger than they were back then. And that's really been permitted, really, by the availability of these very fast GPUs. And also, the third ingredient which you need is lots of training data. And so I'll come to each of these in turn. And I should also say there has been exciting progress on some other AI tasks, which I'll talk about at the end as well. Okay, so just to talk about the data sets for the moment. So one facet of these models is that they do need to be trained in a supervised fashion. I'm going to go into the details of that in just a moment. But these are two examples of sort of modern data sets that were basically collected by using sort of, crowdsourcing on the internet through Amazon Mechanical Turk. So the idea is you're going to have a whole bunch of images and get humans to say what's in the image. Okay, so you can see these things contain millions of examples. These are just orders of magnitude bigger than the data sets that people had back in the 80s, where you had sort of tens of thousands of examples and things like that. Now, the hardware, it turns out that these neural net models are actually incredibly convenient to implement on GPUs, because they basically consist of matrix multiplications and 2D convolutions and things like that. And those can be parallelized very easily, and that's what GPUs are very good at. And so the latest generation of these GPU cards from NVIDIA deliver, huge performance in actually, a fairly small package. So they're, 10 teraflops from one GPU that you see here. And that, just to put that in context, that's faster than the fastest supercomputer in the world in 2000. And it's 10 million times faster than the Sun workstations that the researchers were using back in the 1980s to train those first ConvNets, the convolutional neural network models. So there's really been enormous speed-ups since then. And so using these GPUs and with the big data sets, Jeff Hinton and his group at University of Toronto, Alex Grozevsky and Ilya Sutskever, they, in a seminal paper in 2012, basically came up with this big neural net architecture. So it has 8 convolutional layers. It has, 60 million parameters. And it was trained on this very large ImageNet database from Stanford. And it used a GPU implementation. And the whole thing took, about a week to train on a pair of GPUs. So it's, very laborious. But they got some very exciting results, which I'll go through in just a second. However, I just want to explain, just give you some insight into how these models are trained. So as I mentioned, all these models are supervised. And what that means is as follows. So the idea is, let's just take the image classification task. So in this problem, what you're trying to do is you're given an input image, and you're going to try and predict a label for that image. Okay? So the idea is that you're going to pass this image through your neural net, which has some parameters theta, and you hope that the output from the model should be some label, say in this case abacus. So if it predicts that, it's got this example correct, and you don't do anything. But then you present another, the true label is abacus, and the two agree. Now you present another image during training, and you push that through, and let's say the model predicts zucchini. Okay, well actually the true label was slug. All right, so basically there's some kind of error signal that you can then take, and you can then push this back into the model to update those parameters. So the next time you show an image of a slug, it doesn't say zucchini, it says the correct thing. Okay, and so the idea is you do this, millions of times. You show millions of images like this, which slowly basically update the parameters of the model. And then what you do is you take the parameters of the model and then evaluate them using new examples that it's not seen before. And that's a crucial point. So it's not enough just to memorize the training examples. The models must generalize to things that it hasn't seen before. Okay, so then hopefully when you present these, held out examples, it gives the correct prediction. And the key point, though, is that for each of those training examples, you had to know what the true answer was. Okay, so that's something which the moment is provided by humans. Now, the deep learning models, I just want to contrast them for a moment here with traditional approaches for image classification and machine learning. So in the traditional approaches, what would happen is you would have a bunch of hand-designed features. So these would be things that would be crafted by computer vision researchers that would seem like good things to use, say, for example, edges or something like that. Now, there wouldn't be any explicit parameters in those that would be updated during that training phase. All that would happen is you would take those features, they would take in the image, it would extract the features, and you would have some simple classifier on top of those features that would be trained at training time. Okay? Now, that contrasts with the deep neural net. So what's effectively happening there is that each layer in the net is a sort of little mini feature extractor that extracts successively sort of more abstract representations of the input and goes all the way up, all the way from pixels up to the output label. Okay, so the idea of things, that thing is now going to be trained end to end. So each stage of this is going to be learned. So essentially you're learning which features to extract within the model. And this actually proves to be sort of a crucial thing. It just turns out that human intuition isn't enough to hand design good features. Both, in this case for the image classification task, but as we'll see, also for other domains as well. Okay, so just to show you now some performance, some empirical performance, there's a challenge run by the Stanford folks called the ImageNet Challenge, and they basically ask these models to classify images into one of 1,000 different categories, and they measure the error on an evaluation set. Okay, and so what I'm showing here is the winning performance, the error of the winning performance for each year of the competition. So in 2010, 2011, you can see the performance was around sort of 26, 25%, that kind of thing. And this was using the traditional handcrafted features. And then that paper from the Toronto group in 2012 dropped the performance down to 16%. And people were very surprised because previously these convolutional nets hadn't really worked very well on these complicated images. And what's perhaps even more interesting is in the subsequent years, the communities managed to sort of engineer the architectures of these models to dramatically reduce the performance, really substantially, not just a few percent. You can see now that it's gone all the way down to sort of, I think the latest results actually are better than below 3% error on this metric. And just to put this in context, if you take a human and get them to do this task, which admittedly is a rather artificial task, then you can see they're actually doing, a little bit worse than the best models that we have at the moment. I just want to emphasize, of course, this is a somewhat constrained task. It's much easier than just recognizing completely general things out there in the wild. Now, the question is, what's happened to the architectures to give this remarkable gain over the last 3 or 4 years? Well, if one thing we can do is to look at the depth of the models. So one thing that's happened is that people have figured out how to train much, much deeper models than before. So 8 layers previously was considered very deep, but now the winning model, entries have hundreds of layers of representation within them. And so this is the single factor. It's not that they've increased the number of parameters in the model particularly. If anything, actually, they've decreased slightly. It's really the depth of the model that's been the sort of key factor. And just to sort of give some slight insight into why the depth is important, the idea is, as I mentioned very briefly at the beginning, each layer consists of a simple nonlinear function. And the idea is that when you compose these nonlinear layers, when you compose these nonlinear functions together, they build very complicated functions. And so if you just in this little toy example, I'm showing 2 classes, both some red and blue dots, and we're trying to separate them with some kind of decision surface, which I'm showing here in purple. And if you just have a single layer model, you only really have a straight line that can separate the 2 classes, which clearly is inadequate for this sort of complicated data. But when you have, in this case, a 3-layer model, you can already see that with 3 compounded sort of nonlinearities, you can construct this quite complicated separation between the classes and so on. And so this is obviously a toy example, but if you use some sort of visualization techniques to look at what happens in these big ConvNet models, you'll see they're able to learn some very complicated invariances and things like that. So for example, you find features that correspond to, say, sort of concentric circles, features that correspond to sort of text on the side of objects and things like that. And it's just proven very difficult to actually no one's ever been able to sort of hand engineer features that were able to capture these kinds of structures. And of course, once you have those kinds of features, it's then much easier to build some representations on top that can then classify the class of object. So just to give you some sort of qualitative feel for how well these things work. So this is just looking at a recent one of the state-of-the-art systems running on one of the evaluation data sets. So you can see this is just a typical sort of indoor scene. In this case, the model's outputting a bounding box. They can also actually output a little per pixel mask as well. And there's a little confidence attached to the class prediction as well for each of the boxes. And you can see it captures really a lot of stuff, even for people who are, you can see this person here is quite heavily occluded and it still gets them just fine. It does miss 1 or 2 objects. There's some umbrellas here that it's not captured. Here's another example. You can see some quite different lighting conditions. People in the shadows back here, it can find reliably different viewpoints of say the mopeds it's doing pretty well on, and so on. And then you can also get these models to, this is just showing some latest results from a system from some colleagues at Facebook. So this is a little video processor for each frame independently, where they're tracking human pose and stuff like that. And you can see that they're able to sort of really do a good job of kind of, figuring out the configuration of the person. And this is a more challenging example here. Some sort of breakdancer doing some crazy things. You can see it does lose the tracking at some points, but it still gets it most of the time. So anyway, so these systems have really gone from kind of pretty hopeless performance to actually being working really pretty well. Now the story is actually very similar with speech recognition. So what's remarkable is it's very much the same models that are used, and the story's been very much the same, that these traditional handcrafted features have been replaced with these deep neural nets. And so what you see here is a little plot showing here the sort of technology, the previous technology in blue. This is an error rate, so lower is better, and just showing a plot here as a function of the amount of data that they ingest during training, and then the same curve for the deep neural nets. And what you notice, in fact, you might think, well, maybe these deep neural nets just just need tons and tons of data to train, and it's true, but they do actually still, even with relatively small amounts of data, work better than the traditional methods as well. So just to give you, so this is a snapshot of a kind of state-of-the-art speech recognition system from Baidu. So this thing's a huge system here. In this case, 100 million parameters, 11 layers. It's a slightly different architecture. This one involves a recurrent net rather than a convolutional net. And this is some benchmark comparing here to human performance. And this is an error rate, so lower is better. And you can see that it's getting, at least on these benchmarks anyway, sort of comparable performance to humans. So another domain, which I think is a little bit, there has been great progress, but there's still a long way to go, is natural language processing. So this is, so one example of this would be something like machine translation, translating between different languages. And so recurrent neural net models here have been proven very effective. So the idea is you somehow basically have a recurrent neural net is a type of neural net that can capture the temporal dependencies within the data. So a sentence, of course, is that you can think of as a temporal sequence of tokens, and these models can sort of ingest a sentence and end up with basically some hidden state within the model representing that entire sentence. That's the red blob, and then that is passed to a separate recurrent net, which then transcribes it out to some sort of output representation in a new language, in this case, French. And so again, you see also a plot here where the y-axis here is some measure of translation quality, which is actually quite a difficult thing to measure, in fact. And here we see the sort of performance of different models in some sort of competitions, and yeah, there's a sort of very dramatic increase over time. In this case, on sort of English to German, but in practice, of course, we're seeing similar gains on other sort of language pairs as well. Another task in natural language processing is language modeling. So there's lots of uses for this, but one easy to interpret one is just synthesizing realistic text. And so this is a plot here just showing some sort of measure of quality of the text. And so this is just lower is better, and this again is just looking over time from sort of 2013 to last year. And this is coming down quite a lot. And just to give you a sort of feel for the quality of the most recent models, these are just sort of random burblings from the model. If the model's just free-form riffing, as it were, just generating sentences. And you can see they're reasonably coherent, right? I mean, they're sort of not completely sensical, but they definitely have some look vaguely like English to us. Okay, so of course all these breakthroughs have unleashed a whole wave of applications. Okay, and so just taking the translation one for example, of course probably most of us are familiar with things like Google Translate. That's something which is now able to translate between all kinds of crazy language pairs out there in the world. The quality varies, but it still works surprisingly well in some cases. And then Facebook also has does translations too. So they handle about 2 billion translations a day between 40 different languages, and then it's all using deep nets to do these things. And then in general, of course, the internet companies have deployed these deep nets in a wide range of settings. So I happen to know a bit about what Facebook does. So they have over 1 billion images a day uploaded. Each of one of those goes to 2 of these deep nets, these convolutional nets for recognizing images. One does face recognition to see if there's any of your friends in the picture. And then there's also one that looks for offensive content, nudity or violence, and that also just generally sees what objects are there in the picture, dogs and things like that. So other, of course, applications that you see now, your smartphone uses a deep net to do speech recognition. We see things like the self-driving cars. Of course, there's many aspects to that problem, but of course, one primary problem is perceiving the environment around the vehicle. And so all the latest systems are using basically deep nets for that task. I should also say that there's also been a lot of interest in the last year or two on using some of these models for scientific problems. So particle physicists now are using them for sort of looking through, of course, all the data from these big particle accelerators. I think one area where there's a lot of potential progress is things like medicine. And lots of radiography type tasks, we are looking at scans or images and you want to try and find some sort of anomaly like melanoma or breast cancer. And you also see it in also other settings like in the emergency room, like looking for sepsis, which is something that these algorithms can help with. So just to take a step back and look at, talk about some of the issues involved. So one thing that is very important with these models is the architecture. So previously, the human sort of input went into designing the feature representation. And in deep learning, that piece has been replaced basically by, is learnt now, okay? But the human input still is there in terms of deciding which is the appropriate architecture for the model. And what you find is if you just take a network with completely arbitrary structure, they don't work well. So the particular architecture involved in a convolutional net turns out to be very important for images, and indeed it's been designed to exploit a lot of the sort of structure, the fact you have local dependencies, pixels lay on a 2D grid, or if you're dealing with video, it's on a 3D grid, and things like that. And if you don't adapt the architecture to the domain at hand, these models don't tend to work very well. So I think it's an open question here, how when you're presented with a new domain, how you can sort of automate this process of coming up with a good architecture. So at the moment, essentially it's done by sort of trial and error essentially with graduate students. Or researchers in industrial labs and things. So another thing to mention, of course, is that we don't have a very good theoretical understanding of these models, okay, or any good performance guarantees. And you can imagine, if you're trying to design a self-driving car system, you might really want to have some sort of cast-iron guarantee about, its performance. But it's hard to give with these kinds of models. And but part of the reason is that, these models are very high-dimensional. There's lots and lots of parameters within them. They're also very non-convex, and so that's a big issue because a lot of the mathematical tools we might use to analyze them, unfortunately, don't apply here. So, this is a big sort of open problem. I mean, the good news is there's a lot of very smart theoretical people now thinking about these models, okay, and trying to explain perhaps why, why they work and trying to make predictions about what they might do, under certain settings. It's also worth saying that they're quite difficult to inspect, these models. So, you shove in the pixels at the beginning, at the input, and out pops some, category label for the image. But it's very unclear what's really going on in the center of these models. And so you can't look at, it's very hard to look at an individual, unit in the model and say, this is recognizing a cat or a dog. I mean, you can hand-wavily do it. But this is, in contrast to, other types of machine learning model, like, say, for example, probabilistic graphical models, where each node has a very definite, meaning and instantiation in the world. And then the final point, which I discussed earlier, is you do need lots of labeled data. And that's not always possible to obtain in many domains. And so this brings me on to sort of, I think, one of the big unsolved problems at the moment, which is unsupervised learning. So this is the idea that you should be able to learn, without hand annotations, or maybe from just a very small handful. And this is really, therefore, about capturing the sort of structure inherent in the data. And it's of great practical importance, because what you find is in the real world, there are lots and lots of categories that only appear very rarely. Okay, so what I'm showing here is a sort of log histogram of the frequency of objects in, say, a vision bench data set, and also words in Wikipedia. And what you see, effectively these things are showing you, is that there are a few very, very common words, or indeed object classes, but there's also a very long tail out here. There's lots of classes that you see that really only occur like a handful of times in the entire of Wikipedia, and so on. So it's just this notion of trying to capture millions of labeled examples for every single class just isn't going to be possible. And we need some way of sort of, figuring out how to learn from a much smaller set of examples. And that's when it boils down basically to be able to sort of do this unsupervised learning problem. Now, just one other sort of argument, which I'm just going to sort of slight detour, is that there's a sort of biological argument that, perhaps it seems very unlikely that our brains are purely using supervised learning. There seems to be some sort of unsupervised learning going on, although it's very, very unclear what it might be. So this is an argument from Jeff Hinton. So his argument is that, well, our brains have about 10 to the 15 synaptic connections within them, and we only live for about 10 to the 9 seconds. So somehow we need to sort of get about 10 to the 6 bits of information per second to set these connections. And there's just not enough information from sort of high-level semantic labels. I mean, your mother occasionally says, this is a spoon or something, but she doesn't say this, every few seconds, continuously for your entire childhood. And even that wouldn't be enough to sort of give you, to set all those connections. Okay, so the only source of information, the only source which has enough information is really the input itself. And that's really, so unsupervised learning is really about sort of essentially modeling the input distribution. And so there's a lot of people working on this. It's very unclear, sort of, I mean, there are sort of solutions that work okay, but there hasn't been the same sort of breakthrough that we've seen in, in other settings. So that's one, I think, sort of, big problem that remains to be solved. The other big thing, of course, is that, solving AI is not just about perceiving the world, right? You have to be able to act within it and also reason about the world and also plan. And so you can imagine you've got some sort of AI agent, a robot or something, and it sort of uses a deep net perhaps to perceive the world, but then it must decide how it's going to act to achieve some goal. And the key to doing this really is to be able to predict what the outcome of your actions will be. So effectively, the agent needs to have inside it a little model of the world, so it can sort of, in its mind, try out a few possible sequences of actions and figure out which one it thinks will be likely to, yield some good reward or something like that. And so this building good world simulators is actually another sort of big area of endeavor at the moment. And I just want to sort of, this is a good point to discuss, one example of, being able to sort of plan and reason in the world is Google's AlphaGo project. So this was trying to design a computer to play the game of Go, which is much harder than chess. So they essentially used combined deep learning with some kind of classical tree search techniques, trained it with lots and lots of data from expert play and also self-play, where the machine will play against itself, ran on huge numbers of GPUs, but they built some incredible system that could actually beat the world champion recently. And this was a huge event, certainly in Asia, where Go is a very much a widely played game. Now, while this was a very impressive feat, it's important to realize that in Go, the world is completely visible and deterministic. That is, if I place a new stone down in a new position, it's completely clear, if that's my action, it's completely clear what the new position of the board will be. There's no uncertainty, it's no sort of, it's completely visible as well. So you'll see all the consequences of your actions. Now, of course, the real world is just not like that. Okay, so in the real world, of course, there are many other, you might try to go turn left, but maybe your car doesn't quite make it, or maybe there's some other car in the way, and so on and so forth. So, building general predictive models of the world is another big research, endeavor at the moment. And so, people are trying to do this with natural video, trying to predict subsequent frames. I was involved with some small project just trying to predict sort of trajectories of wooden blocks falling and things like that. And there's a lot of recent work, from labs at Berkeley, DeepMind, Facebook, and so on this kind of problem. Once you have a good forward model like that, you can put it into sort of planning algorithms and try and get your AI agent to reason about things. Okay, so that's another sort of big area. Now, I've actually gone a little bit faster than time, so I'm just going to wrap up, but I'm very happy to talk more about other unsolved issues. So I think there has been a lot of great progress on these perception tasks, and the many practical applications that just didn't work now are possible, and used millions of times a day by companies around the world. But there's a lot of algorithms that we're missing. We still have sort of fundamental scientific roadblocks we need to overcome to be able to tackle other tasks in AI. Okay, so unsupervised learning is one I mentioned, predictive models of the world, as also touched on. Other things like program induction as well, or some aspects of reinforcement learning as well, I think are also very fundamental to progress. And so there's essentially, the high-level message here is there's still many unsolved problems, and there's no true timeline really for obtaining true AI in the general sense of it. So I'll stop there and happy to take questions.
Okay, so any questions for Rob Fergus? If you have any, yeah, go ahead. If you could step to the mic in the center, that'd be great. Thank you.
Sure. If you could just expand a little bit on when you said that in the deep learning model, right, the features at kind of the intermediate layers are not predefined, they're not selected by humans. Yep. What actually is happening in those middle layers? When you think of a simple data set where we hand tag it and create the attributes, what's actually happening in the middle layers?
Well, that's a great question. Well, so strictly speaking, it's hard to say exactly. I can give us a hand-wavy answer, and it depends very much on the domain at hand. So the idea is that you would want to be so it's easiest perhaps to think about this from the point of view of images, which it's easy to visualize things. And so those these little plots I was showing at the bottom here, these are just showing you little image patches that cause one particular intermediate feature map in one of these big deep nets to activate very strongly. Okay, so these are sort of patches, if you like, that particular part of the model really likes. Okay, so in this case, it's learning some sort of mid-level feature, I think is the term that people would use in computer vision, which is essentially sort of text on the side of things. And this is another one, a separate feature map, but this one seems to really respond strongly to kind of concentric structures. And you can see there's a wide variety of kind of backgrounds and things, but it's that sort of concentric circle structure that it seems to respond to. So the answer is, in general, it's hard to say. You can try these sort of tricks of kind of take inputs and see which types of input get a particular part of the model to respond strongly. In general, as you take these deep nets, the first layers will be finding edges. The second layers find sort of conjunctions of edges. The sort of middle layers have these sort of mid-level concepts of sort of parts of object and things like that. And then the higher level features tend to be more object specific. So you'll find in these models there'll be high level features which will respond very strongly to, say, Alsatian dogs, or to plants or something like that, or flowers. And so yes, but that again, it's very dependent on the data set and also the domain that you're in as to what these things will learn.
So feedback on the actual prediction.
That's correct. That's correct. So that's one of the remarkable things, that you can propagate that feedback through 100 layers of representation. And there's some very interesting math as to why you can. I mean, the latest models have been designed very carefully to ensure that that signal can be pushed all the way back.
Other questions? Yeah. Stepping to the mic.
Hi, you mentioned earlier one of the issues with AI currently is the lack of label training data.
Yeah.
Would you mind just discussing recent pushes toward developing label data, specifically with effect to black swan events or events where there is lack of evidence for?
Right. So actually, the black swan event phenomenon you're referring to is. So let me just find my thing. So this is actually what I was trying to show in these plots here. So these are sort of very rare events that only occur occasionally, but I guess obviously in the black swan scenario, they have outsized impact on the particular system that you're concerned with. So there's a lot of efforts to label data in the world. The catch is that these models. Well, first thing to say is that the big models still need a ravenous amount of data. Millions of examples to be trained effectively, and you typically see the performance just increases, continues to increase as you collect more and more data. You can train these things also from noisy sources. So if you take images, say, for example, on social media platforms, users often provide hashtags for images. So those are sort of automatically provided by the person who uploaded the image. You can train on those. They won't be as effective as having completely clean labels, but you can train effectively on them. If you have these very rare events, well, that's really a bit of that these very rare classes or very rare situations for which you just simply cannot get many label training examples. Well, that's actually one of the sort of open research problems, is how you can sort of how you can generalize. The hope would be that you use your plentiful data, for which you do have lots of label examples, to build a good representation for that domain. And then once you have that high-level representation, then you can afford to train a sort of very lightweight detector for your black swan event on top. Okay, so the hope is that that black swan event still should be somehow representative. It should be somehow in the same domain as the other data for which you have perhaps thousands or millions of labeled examples. But it's definitely an open research problem as to how to do this effectively, right? This is so-called one-shot learning or low-shot learning, as it's called. How you can train from these just one or two examples. So,
other questions? Now, I actually do have a question. So maybe, John, do you have one?
Perhaps you can hear me. That many of the applications to which we will apply artificial intelligence will be critical importance, and errors are not going to be acceptable. Yeah. So in a situation where we can't inspect in detail the process leading to a conclusion, we need to learn methods for developing trust in the outcome.
Yeah.
Talk to them.
Yeah. I mean, that's a very interesting point. I mean, there's a sort of interesting dilemma. Would you rather have a system that on any objective test you give it performs better, but you can't explain exactly how it works, or would you have something that works less well but is explainable? And so that is, it's not. I'm not quite. I mean, that I think depends on, the application at hand. I think it is a big open question as to exactly when these models will fail. Indeed, there's a little sort of small area of research in constructing pathological inputs for these models that will cause them to fail in very unexpected ways. You can take an image of a giraffe or something, add some very carefully designed noise, and suddenly it'll think it's a flamingo or something like that. Okay, and so it's not quite clear whether these things are fully practical in the real world. I mean, people have been trying to push these so-called adversarial examples in that fashion, but it's a bit of an arms race in some sense, because you can try and design these networks so that they won't be fooled by them. So that's one particular aspect, sort of creating sort of sensitivity to pathological examples. But in terms of giving hard guarantees that this network will fail 1 in 10 million times or something like that, which is what you might want for a self-driving car. Unfortunately, it's other than gathering a data set of say 1 trillion examples, running it through and just checking your error rate is less than 1 in 10 billion or something. There's no theoretical way you can show that at the moment. I mean, maybe people figure these things out. I mean, this has a lot of implications for things like self-driving cars, right? Because you have very few training data of like people driving into a ditch or something, but you certainly need to be able to recognize when that's happening, with a car, and you certainly would like some reassurance that this thing is going to be able to, not crash in unexpected situations.
Maybe I'll ask one final question, and we can explore this a little bit more on the panel discussion. But as you describe these models, they largely come across as a black box. and maybe multiple black boxes. One black box leads to another black box. So we really don't understand what's going on. So when it misclassifies, a slug versus a zucchini, it really doesn't know anything about vegetables and about slugs or baseball bats or, whatever. What are sort of the implications for the possibilities of misuse, given the models really don't understand anything?
Right. So it depends what you mean exactly by misuse, I suppose. I mean, they don't have any common sense, if that's what you mean. So that they're this just to the introduction. They're very narrow in the sense all they're doing is just learning how to sort of give a correct label for an image, right? So so certainly if they're deployed in settings outside of that, then yes, I mean, all bets are off exactly as to what they're going to do, I would say. So I mean, that in general is the problem, that if the distribution of data changes from when you train the model, then you're in trouble. I mean, there are techniques that people are working on, so domain transfer and things like this, to sort of adapt and make models more robust to that kind of thing. But yeah, I mean, it's a bit unclear how to do it exactly.
Okay, so we'll pursue in the panel discussion how to endow some of these models with some common sense. Okay, so please join me in thanking Rob. Okay.